Thank you, Ronald. Welcome everyone to the fourth data structures workshop. If you missed the previous workshops, you can find them on our YouTube channel, Hyperion Dev. You can, like and subscribe, and please share the video. And let's get started. So today I'm just going to recap all of the data structures that I've covered so far and provide you all with some real world examples and use cases of these data structures since I've gone through, explaining what they are. Now we're just going to dive into, what can we actually use what can we actually do with these data structures? And then I'll end off with just giving you guys some project ideas so that you can, further your own learning and knowledge on data structures. So, firstly, what is a data structure? So, a data structure is a particular way of organizing data in a computer so that it can be used effectively. So I've been, so you can see this image over here. We've gone through pretty much all of the data structures that's been covered here. Just the importance of, the data structures is that it is the most fundamental building block concept in computer science. So a good knowledge of data structures is a must to design and develop a efficient software system. So over here is the list of what I'll be um, what I'll be covering today. So you can see we'll go over arrays, linked lists, stacks, queues, trees, graphs, hash tables, and matrices. Okay, so first, just a quick recap of what an array is. So an array is a collection of items stored at a contiguous memory location. So we have two different types of arrays. So we have static arrays, which have their size or length determined when the array is created or allocated. For this reason, they may also be referred to as a fixed length array or fixed array. Array values may be specified when the array is defined, or the array size may be defined without specifying any of its contents. So depending on the programming language, an uninitialized array may contain default values, or it may contain whatever values were left in memory from the previous allocation. Next, we have our dynamic arrays, which allows elements to be added and removed at runtime. So most current programming languages include built-in or standard library functions for creating and managing dynamic arrays. So, what are the real world applications of arrays? So, firstly, you can use it for, in an arrangement of a leaderboard of a game. It can be done simply through, just an array to store the scores and arrange them in descending order to clearly make out the rank of each player in the game. We can also make use of 2D arrays, or commonly called matrix, which are used in image processing. Um, is also used in speech processing, in which each speech signal is an array. Next, the contact application in our phone, which we use in our daily life, has a lot of contacts. So these contacts are stored in the form of an array, so we can add or delete contacts as we see fit. And lastly, similar to song list, similar to a contact application, we also have like something like a music application, which can store songs in a playlist using an array. Next, we have linked lists. So a linked list is a linear data structure in which the elements are not stored at a contiguous memory location. So the elements in a linked list are linked using pointers as shown in the image. So a node may contain two fields, i.e., the data stored at that particular address, and the pointer which contains the address of the next node in the memory. So the last node of the list contains a pointer to null, as you can see in the image. There are also other types of linked lists, like doubly linked lists and circular linked lists. So let's dive into what applications, what use cases they are for these linked lists. So, firstly, images are linked to each other. So, an image viewer software uses linked lists to view the previous and the next images using the previous and next buttons. Web pages can be accessed using the previous and the next URL links, which are linked using linked lists. And next, similar to the previous one, music players also use the same technique to switch between music to keep the track of which um, sorry about that. It can also be used to keep track of um, multiplayer games, so a circular linked list can be used in that case. And lastly, the undo and redo or delete operations on some like text editors make use of linked lists. Next, we have stacks. So a stack is a linear data structure that follows a particular order in which operations are performed. So the order may be last in, first out, or first in, last out. You can think of a stack data structure as the pile of plates on top of one another. So with it, you can put a new plate on top, and you can remove the top plate. And if you want the plate at the bottom, you must first remove all of the plates on top. This is exactly how stack data structure works. So in programming terms, putting an item on top of the stack is called push, and removing an item is called pop. In the image, although item 3 was kept last, it was removed first. This is exactly how the last in, first out principle works. You can also implement stacks in um, any programming languages like C, C++, Java, Python, or C Sharp, but the specification is pretty much the same. So here are some use cases for stacks. So image logs and all messages you get can be arranged in a stack. Um, so call logs, emails, Google Photos, any gallery, um, like YouTube downloads, those things can be saved in a stack. Next, we have history of visited websites can be stored in a stack. Um, Syntaxes in languages are parsed using stacks, and converting infix to postfix expressions also make use of stacks. Next, we have queues. So queue is also a linear data structure which follows a particular order. In this case, it is first in, first out. A real world, just a quick example would be a single lane or one-way road where the vehicles enter first would exit first. Um, Other types of queues would be like circular queues, input restricted queues, output restricted queues, and priority queues. But pretty much all that I've mentioned, also for the previous um, data structures, I have explained in the previous workshops, which you can find on YouTube. So use cases for queues. So we have operating systems use queues for job scheduling. It's also used to handle congestion in network queues. Data packets in communication can also be arranged in a queue format. And while switching multiple application windows, that makes use of circular queue. And lastly, it's also used in call centers where calls of people are put on hold while the person is in another call. The next data structure we have here is trees. So a tree is a non-linear hierarchical data structure that consists of nodes connected by edges. When actions are performed in a linear structure, the complexity rises as the data increases. On the other hand, the tree data structure provides much quicker access to data which is nonlinear. Um, the data structure is called a tree because it resembles a tree as you can see in the image. It starts with a root node and branches off with its descendants. So, use cases for trees. So, um, XML parsers use tree algorithms to um, sort that out. Next, we have um, decision-based algorithms um, used in machine learning, which works on upon the algorithm of a tree. Domain name servers also use tree data structures. Next, our file explorer or any like file system on your mobile phone also makes use of trees. Next, implementation of navigation in the websites or applications also makes use of trees. And yeah, it is very common used when you come across decision making steps in games. Next, we have graphs, which is a data structure which is also nonlinear and is made up of finite number of nodes or vertices and the edges that connect them. So in my previous workshop, we went through a couple of types of graphs, like the undirected graph, which is what is displayed in the image or on the slide. Um, in an undirected graph, nodes are connected by edges that are bidirectional. For example, if an edge connects node 1 and 2, we can traverse from node 1 to node 2 and from node 2 back to node 1. There's also directed graphs. So in a directed graph, nodes are connected by direct edges. They can only go in one direction. So for example, if an edge connects node 1 and 2, but the arrowhead points towards 2, we can only traverse from node 1 to 2 and not in the opposite direction. So some use cases for graphs would be Facebook's Graph API makes use of graphs. Google's Knowledge Graph also makes use of this data structure. It is also used in Dijkstra's algorithm or the shortest path first. Algorithm uses graph structure to finding the smallest path between the nodes of the graph. It's also used in GPS navigation system, to find the shortest path. It's also used in various e-commerce websites for user preferences. And lastly, it can also be used for resource management in an organization. The next data structure, which I haven't actually covered, um, which we can definitely research, is hash tables. So hash tables are stored. Um, well, they store data in key value pairs, so we can only store data which has a key associated with it. So some uses for hash tables: data stored in a database is generally of key value format, which is done through hash tables. Message digest, a function of cryptography, also makes use of hashing for creating output in such a manner that reaching to the original input from that generated output is almost next to impossible. Next, every time we type something to be searched in Google Chrome or other browsers, it generates the desired output based on the principle of hashing. And lastly, it in our computers we have various files stored, in it. Each file has two very crucial information, that is, the file name and file path, in order to make the connection between the file name to its corresponding file path. Um, ha- File path, which makes use of hash tables. Next, we have matrices, which is an ordered collection of columns and rows of elements. Um, s- you can see it does resemble closely to a 2D array. So use cases for these matrices: in geography, matrices are used for making seismic surveys. It's also used for plotting graphs, statistics, and also to make scientific studies and research in almost, in different fields. And lastly, matrices can be used in representing real world data like the population of people, um, and things like mortality. All of that can actually be represented with matrices. So, yeah, here are some project ideas that you can do, just so that you can solidify your knowledge on these different data structures. And it's a really good thing to research, just to expand your knowledge. So firstly, for arrays, you can try and implement the other data structures like linked lists and stacks. um, a, a project for linked lists could be also something like a student record management system, which makes use of the linked list. So you can have functionality like insert the student record, delete the student record, show student record, and search student record. And you can save information about the student, like the name, enrollment number, the course in which the student is enrolled, and the total marks of the student. Next, for stacks, you can look into a stack-based text editor. So your program will allow the user to, you know, move the cursor and modify the text using the following 5 operations. So things like left, which will move the cursor to the left 1 character, or do nothing if it's at the end of the line. Um, and then there's right, which would just do the other thing, but in the different that in you know in the other direction. Then there will be R delete, which deletes in characters to the right of the cursor. And then we also have L delete, which will delete a character to the left of the cursor. And lastly, we have insert C, which will insert the character C just before the cursor. For queues, you can try implementing various kinds of queues. Um, um, different types of queues. In particular, you can try to implement it using 2 stacks. Next, with trees, I highly recommend that you do have a look at our tree workshops where I explain all this different traversals, and you can try to implement it yourself and try to print the pre-order, in order, and post traversal of a tree. Next, for graphs, you can try to implement Dijkstra's algorithm, which is will give you some good practice in working with graphs. And yeah, that's pretty much it.